two.
Two?
She's Dennis and Toby.
Yeah, but who's the other?
Isa, Sherry. Yeah,
Never.
we have two. I mean,
Very good.
our chances are natural. It's not hobby for the,
Yeah.
the girls.
Well, here we go.
That's cool.
My wife, what are you doing, baby? All right. If I get a phone call, I will rush out of here. It means my wife feels like she's going to pass out imminently.
Okay.
Let's pray. Father, please be with Taylor. Help her to feel better, Lord, and to not pass out and to be well, Lord. Be able to keep me here and to teach, as this is something that's very necessary also. Father, pray for our students. You help them to understand all of this about ionic and solid crystal radii and unit cells and packing and density and area and volume, Lord, and help me to make all this clear. Help it to be clear to me. Father, we ask this in Jesus' name. Amen. All right. Well, where did we leave off? I've been a couple of miles since then, I guarantee.
We're doing, if my notes are not wrong, we did the center, face center cubic.
Did we do the problems associated with it?
I don't
Or did we just talk about it?
Well, I think we just talked about it.
Okay. We have problems associated. Okay, hold on just a second. You have a problem about polonium atoms, we did that, right?
Yeah, colon B.
Okay, there's face centered. Okay, no, we did that. We did that. This must be where we're at. Calculating atomic radii and density for metals, part 2. Sounds fun, right? All right. All right, quick review, because this is going to matter. When we talk about this face-centered, okay? So, all right. So we've got one. I didn't draw that very well, did I? Maybe that's not so bad. You've got basically half of an atom on each face, okay? So I expect to have half of one here, half of one here, half in the back, half down below, half on this side, okay? And you know, if I were to draw that 3D, it looks kind of something like this. And then I also have an eighth of one in every corner. And I've got 1, 2, 3, 4, 5, 6, 7. So I've got 8 corners of 1/8, right? And I have 1, 2, 3, 4, 5, 6 sides of 1/2, right? So this is 3, this is 1, that means these have 4. You think in terms of density, you're talking about having 4 atoms per unit cell. okay? That matters for where we're going with the rest of this. Another thing to pay attention to is, and I didn't draw it very well, but these actually are touching, okay? This is as tightly packed, this is as dense as we can possibly get it. Every atom is in contact with another atom. All right. Not well drawn, but the best I can do. Okay. So, calcium crystallizes in a face-centered cubic structure. The length of its unit cell is 558.8 picometers. So 558.8 picometers. All right. What is the atomic radius of calcium in this structure? So that's our first part, right? So, you got a thought about taking a stab at it?
Oh, remember that we did the volume of the cube,
Okay.
but we converted the picometers to centimeters cubed.
Okay.
That's the first thing.
Well, we're not doing volume yet. Now I want to know, it's asking us essentially, isn't it asking us for the radius? Yeah, what is the atomic radius? So we want to know what is this here, right? So how am I going to determine that?
So it's going to be half of the size of the.
Half of the diameter?
Yeah.
Okay. Any other thoughts and strategy here? Because I can't get it with that.
Yeah. I think
What I have is this. I know, let me redraw this and it may help. I know this is 558.8. I know this is 558.8. I know this is a right angle. Right. Okay. And I've got this. And I've got this. And I've got this. Here. Right. And I've got this. These are all touching, right? Okay. And really what I want to know is this. Or this. Or this. Or this. Right? I don't have this. I've got these.
So you can find that and divide by 4.
Yeah. So basically I've got a right triangle, right? So I've got a squared plus b squared equals c squared. So I can take my a squared plus b squared, I can square root it, I can find out c, right? But I actually need 1/4 of this, right? So another way I could write this is to say a squared plus b squared equals 4r squared, right? Because my c is equal to my 4 of my radii. Let me just make that real clear. A squared plus b squared equals c squared. I can substitute for my c squared 4r squared, right? So I'm going to roll with that. A squared plus b squared equals 4r squared. My a and my b are 558.8, right? So I have 558.8 squared plus 558.8 squared equals, sorry, this should be in parentheses here, 4r squared, because it's equivalent to my c squared. So I'm going to go ahead and write this out. I'm going to say equals 6, well, yeah, I'm going to go ahead and skip. I'm just going to go 16r squared, okay? All right. I want to solve for r, so I'm going to simplify this. I'm going to say 2 times, because they are the same, 558.8 squared plus 16 equals r squared. Now to find r, I got to square root this, right? So,
It's not divided by 6?
oh, I'm sorry. Yes, it is. I'm looking at it going, that ain't right. Why did I do that? Divided by 16 equals r squared. So now I'm gonna come and I'm gonna put 2 times 558.8 squared over 16 equals R, right? So throw that into a calculator. You probably already did it, right?
I just need the square root now.
Okay, 558.8 times 2 equals divided by 16 equals and square root. Oh, now it wants me to do the whole thing. Okay. My goodness. 2 times 558.8 divided by 16 equals, did you get 8.36-ish? Or did my calculator go crazy?
I got 197.56.
And that is the right answer. I don't know what's happening with my calculator, but it did not like things. 197.6 picometers
Yeah.
is my radius, right? Okay. Now, we're going to go ahead and we're going to do a density with this. So we want mass per volume, right? And it wants our units in grams per centimeter cubed. So it'll help to convert my picometers into centimeters right now. Okay? What you got? It's pico 10 to the negative 9.
10 to the negative 10. I got
I
197.
thought that was angstrom.
Yeah, 197. 1. Point 976. 10 to the negative 8.
Is that right?
It's 1.976 negative 8.
I'm throwing this in the calculator. Give me 1 second. So 197.6 picometers to centimeters. That's right. There we go. So, oh, I wrote it
Yeah,
down wrong, right? So 1.976 times 10 to the negative 8 centimeters. Okay. So we're going to hold that number in mind. Now, we're looking for density equals mass over volume. I'm going to erase this because we're going to need it, the space. All right, so we're going to start with our mass. So we're dealing with face-centered, right? So this is where this comes in, our 8 corners or 6 sides. This is 4 atoms, right? We have 4 atoms worth. 4 atoms of what?
Sodium?
You know,
No,
calcium.
it's calcium, sorry.
4 atoms of calcium. All right. Okay. So we need to get from 4 atoms of calcium to
Or more.
the mass of 4 atoms of calcium, right? So I got 4 Ca, right? Times, let's go with a molar mass. What is 1 mole of calcium?
It's 40.078.
78, and that's grams per mole, right? Okay. Now, so right now I have atoms times grams per mole. I need to get rid of atoms and moles, right? So I should be able to do that in one fell swoop. I can go 1 mole
Yes.
over Avogadro's number, 6.022 times 10 to the 23rd, is that right?
Yeah.
Atoms of Ca per mole of Ca per mole of Ca, right? These will cancel, I'll be left with grams, that'll be good. We can go ahead and tidy that one up real quick. All right, what'd you get?
I got 2.66 times 10 to the negative 22.
That's right. So we have 2.662 times 10 to the negative 22nd grams. Look at mass of volume, our volume. We have one side, right? So, and we know it's a cube, so they're all the same. So I have 1.976 times 10 to the negative 8th cubed, right? So I divide that by that.
Did you get the answer?
I should get the answer. This, by the way, should come out to 1.745 times 10 to the negative 22nd centimeters cubed is the volume. So I divide that by that. I get
I got 3.63 times 10 to the negative 21.
should be one. Well, that doesn't. Something's off. Look at how we've got negative to the negative 22nd divided by to the negative 22nd.
I know what I did wrong.
Okay.
Yeah, that's right.
Okay.
Because I put it positive 22, and that's why I did it wrong.
No worries. Well, let's do another one here. Erase this real quick. All right. Silver crystallizes in a face-centered structure. The edge length of this unit is 409 picometers. Okay. First of all, what is the atomic radius of this structure, right? So we're going to have the same idea here. So we have 409 squared plus 409 squared equals 4r squared. Right, so I can simplify that. Say 2 times 409 squared equals 16r squared. I go 2 times 409 squared over 16. If I want to combine a couple steps, then I can say this equals r squared. I'm sorry, equals r. So, see if I can use my calculator properly this time. What'd you get there?
144.6.
Good. Okay, so my radius is 144.6 picometers. Right. All right, it likes that. Now we need to convert that into centimeters. So we get what? 1.446 times 10 to the negative 8th, or was it?
Yeah.
The negative 8th centimeters. Okay. You want to confirm that? You would not trust me. I'm not trustworthy on these things.
It's to the -7.
Negative 7? Okay. You feel good about that? Okay. 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 So now we're dealing with silver, right? So we want to find the density of this crystal. Right. So we need, it's forming in this face-centered shape. We know, right, that leaves us 1, 2, 3, 4, 5, 6 times 3 is, or times half is 3, plus the 4 corners, it leaves us 4. So we have 4, what are we dealing with here? Ag atoms, right, times, we need to go, let's go molar mass. So what's the mass?
107.87.
7.87 grams per mole of Ag. Now we need to go 1 mole of Ag has 6.022 times 10 to the 23rd atoms of Ag, right? And this will give me mass of silver. What'd you get?
7.377 10 to the negative 9.
Will you run that again? I'll run mine again also.
Yeah, I got 7.18 times 10 to the negative 22.
Okay, so we're in the ballpark.
Mm-hmm.
All right, good. Okay, now that's our mass. We need to divide it by our volume, which is going to be this number cubed, right? So this over 1.446 times 10 to the negative 7th. All right, so let's go ahead and do that. We're relying on your calculator.
I got
I invested in the wrong ones. What do you got?
I got 0.237.
Yeah, you're right. Well, let's focus on this. What is 1.446 times 10 to the negative 7th cubed? And maybe the problem is I didn't put the cubed up there. That may be why I messed that up.
Let's see. It's 3.023 to the times 10 to the negative 21.
21. Okay. All right, so let's divide that by that. Syntax here. Are you serious? What do you get?
I got the same answer.
You got the same answer. We should be at 10.5 grams per centimeter cubed. Well, we have done messed up something somewhere.
casserole.
Not this.
Oh yeah. We used the wrong.
Okay, 409 picometers put into centimeters is 4.09 times 10 to the negative 7th or 8th.
It's 4.09 to 10 to negative 8.
Negative 8. Okay.
Oh,
Okay, we want this number cubed. All right, and now we will get the answer that we should have. Like, I did it 20 minutes ago, I had the right answer. What's going on? I just don't know about this calculator, man. I need to watch a tutorial on how to use it or something.
Now I got it right now.
What'd you get?
10.47.
10.47 grams per centimeter cubed. Okay. All right. Well, there we go. Right numbers always help. Now you understand why I never trust me and I run every calculation 3 times. It's too easy to do all that work, put in one wrong number, have one wrong calculator stroke, and miss everything. All right. Well, here we go. What am I trying to do here? Here it is. Ionic crystals. So we've been doing metallic crystals, right? Now we're doing ionic crystals. Ionic crystals consist of 2 or more different kinds of ions that usually have different sizes, right? You think about an ion, so you have cations and anions. An anion has a negative charge, a cation has a positive charge. This has a positive charge because I lost an electron. I lost an electron, you know, I usually got down to, it didn't just, if I had 1 in my valence shell, then that completed it and I lost a whole valence shell. Reduced my atomic radius considerably, right? Whereas over here it's going to grow slightly due to that repulsion. So, typically, large anions, significantly smaller cations, not always the case, but typically. Most monatomic ions have charged spheres, and their attraction for ions of opposite charge is the same in every direction. So most monatomic ions, so we're not talking something like sulfate or sulfite, where it's, you know, but monatomic, it's got a charge that's radiating equally in all directions. Consequently, stable structures for ionic compounds result from. So we're going to look at this. Stable structures in ionic compounds result from or result in? We're going to say from. Or when. Either way, doesn't matter. When ions of one charge are surrounded by as many ions as possible with opposite charges. So, number 1 is ions of a charge. Are surrounded max ions of opposite charge. So if you're positive, you want as many negative around you. If you're negative, you want as many positive around you, right? You want to maximize that charge. And the second rule is somewhat similar to it. You really want cations and anions in direct contact. It also means you don't want cations and cations in contact. You want anions. They want to orient themselves in this way, right? These two go hand in hand. Structures are determined by two principal factors. So two principal factors. For ionic structures. Okay. Number one is the relative sizes of ions. And number two is the ratio of positive to negative ions. Right?
Yeah.
In simple ionic structures, we usually find the anions, which are normally larger than the cations, arranged in a closest packed array. And it says what that is. The smaller cations commonly occupy one of two types of holes. The smaller of the holes is found between 3 anions in one plane and 1 anion in an adjacent plane. The 4 anions surrounding this hole are arranged. Here's the If I had 4 of these like this, okay, and I want another layer of these on top. That layer to be as tightly packed as you can, it's not going to sit right on this. It's going to be slightly offset. So actually there would be one. Let me draw it like this. The tightest I can pack these is not them stacked on top of themselves, it's actually offset slightly. So it would be like this. Does that make sense?
Like when you do like a pyramid,
Yeah.
and you just like,
Yeah.
like a,
Yeah. So we're looking at filling the spaces between. Well, now, because when I'm doing this array, I've got 4 on bottom, right? And I've got 1 on top. I'm looking at this 1 unit, right? Okay? Which gives me exactly 1 space in between these 4 and this 1 on top, right? And it's not a big space. It's a small space, but I've got large anions, and in this case I'm dealing with a small cation. So if you were to look at things from the perspective of that cation that fits in the space in between, here it is, okay? And it is surrounded by one on top, right? And then one here, one here, one kind of here, one kind of here. Okay, that makes sense? Okay. So it's got 1, 2, 3, 4, 5. Is that correct? I believe that's correct. I believe that's the way to represent this. Of course, they never actually do show it in a way that's very helpful, which is a shame. Okay. I said that all backwards. It's 3 and 1. I drew the whole thing wrong. Considering it this way. The other comes up, but it's not yet. Okay, so I've got 3 and then I've got 1 on top. And I've got room for 1 anion in the middle. Okay. If I were to draw this out again, it looks much like how we had our tetrahedral before. Which is why I went and grabbed those balloons and I'm like, wait, something's not adding up. I got 1 on top, right? And so you essentially have your anion at the knots of these things in this space in between the balloons, and you've got these 4 things. Well, what shape does this form?
Tetrahedral.
Tetrahedral. So this is called a tetrahedral hole, right? So when I have large, say 4 large anions plus 1 small cation, I get a tetrahedral hole model. Book does not do a very good job with this. It's going to give you a bunch of drawings that I don't think are going to help you at all. Certainly not to see each individual hole. This is frankly a much, much better picture of what's going on. And then there's the octahedral hole. So what happens if I don't have 4 large anions and I have 1 small cation? What if I have a larger cation, right? Well then, what if my cation is just, what if I just need more space? We want to pack as close as we can, but if this is too big, like I could not have packed a very big one in the space of that tetrahedral, right? So we've got to go to another, it's going to shift naturally to another pattern based on our rules, right? Our relative sizes of our ions, that's probably number 1, and then the ratio of the 2 together is number 2. So The larger type of hole is found at the center of 6 anions, 3 in one layer, 3 in an adjacent layer, located at the corners of an octahedron. This is called an octahedral hole. So this is if I have 6 large anions and 1 larger, or we'll say 1 large cation. Okay, then it's going to form an octahedral hole. Okay, structurally speaking, what we're looking at is something like this. And I have to offset these. And so basically, because I can't draw perfectly, we understand that it looks like this. I've got 3 in one layer, and I've got 3 on another, and the space in between is the space for my anion. Now when I look at it like this, it just looks like a weird cube or something to me, right? But if we can easily think of it how we did before, as an octahedral shape, right? So I've got these would each be the octa doesn't come from the number of atoms, right? Because I've got 6 plus 1 in the center. So 7 ions, that doesn't add up to an octa, and I certainly don't have 6, you know, I could think tetra here from the 4, but I can't get to octa from this. Each of these is the vertex, a vertice, right? So I got 1, 2, 3, 4, 5, 6. I'll have, that's the number of vertices for an octahedral shape, right? 1, 2, 3, 4, 5, 6, 7, 8 is how they get there. So this is an octahedral hole. What matters right now is that we understand 4 and 1, or we understand, or sorry, 3 and 1, or we understand 3 and 3. But what's going to determine which one it comes from is going to be the size of this cation, right? And there will be times that we don't fill those holes. In certain cases, you've got multiple, and there will be a hole that's not filled at all whatsoever. And we'll be dealing with that coming up. So, that went, other than misdrawing the first time, that went a little better than I was expecting to. All right. Well, let's do a little something with this. All right. Zinc sulfide is an important industrial source of zinc and is also used as a white pigment in paint. Zinc sulfide crystallizes with zinc ions occupying 1/2 of the tetrahedral holes in a closest packed array of sulfide ions. What is the formula for zinc sulfide? Okay. So we have zinc, and we have sulfur, right? Details that told us about this is that it forms tetrahedral holes. Right, and that my zinc occupies 1/2 of them, right? you some information I didn't give you yet. Sorry. Okay. Depending on the relative sizes of the cations and anions, cations of an ionic compound may occupy tetrahedral or octahedral holes. Relatively small cations occupy tetrahedral, larger occupy octahedral. If the cations are too large to fit into octahedral holes, the anions adopt a more open structure, such as simple cubic array. The larger cations then occupy the larger cubic holes, made possible by more open spacing. There are 2 tetrahedral holes for each anion. Okay, so this part you have to know. 2 tetrahedral holes per anion. In either HCP or CCP arrayed anions.
Coach, I'm here for you. I just got it. I've been looking for you. Come on.
It's not quiet.
Coach. How can this do both?
So in other words, we have a max cation to anion ratio of 2 to 1. 2 positives to every 1 negative. Right? So we'll roll with that information
Okay.
for this, okay? So, zinc fills half of all the holes. Well, I've got a max of 2 to 1, right? So, zinc equals 1/2 of 2 holes per sulfur. Well, zinc times 1/2 times 2s equals s.
Gel?
So my formula becomes, that's ultimately what this is. It wants us to tell us,
Yeah,
tell the formula.
Right to one.
Okay. There we go. Let's do it. I don't know what my life's going to be like when I don't have all these Portuguese-speaking young men around me. Never in my life. I knew exactly one person who spoke Portuguese before this year. And that was a long time ago. All right. Next one. Lithium selenide. Can be described as the closest packed array of selenide ions with lithium ions in all the tetrahedral holes. So what's the formula?
2 to 1.
2 to 1. Okay. The ratio of octahedral holes to anions. So it is 1 to 1. All right. Sapphire is an aluminum oxide. Aluminum oxide crystallizes with aluminum, so this is aluminum plus oxygen. Crystallizes aluminum ions in 2/3 of the octahedral holes in the closest packed array of oxide ions. What formula is aluminum oxide? Okay. So aluminum in 2/3 of the oxygen holes. Okay. So we know that our max is 1:1. So aluminum equals 2/3 of oxygen, right? So when I want to write that out in empirical formula, it would be Al 2/3 O, but that doesn't really work. So I need to multiply the whole thing by 3, right? So I get
AL.
multiply by 3.
ALT O3.
O3. Okay, simple enough. Just conceptual stuff here. Next one. The white pigment titanium oxide crystallizes with titanium ions in 1/2 of the octahedral holes in a closest packed array of oxide ions. So we've got Ti plus oxygen. It is in 1/2, so titanium equals 1/2 of oxygen, right? So I can go temporarily titanium 1/2 oxide, but that ultimately doesn't work out. So I need to go titanium dioxide, right? Okay. All right, good. Let me erase all that. And I'm sure we're going to get to do some other calculations. How do I know if it's going to be tetrahedral or octahedral?
The size,
Of?
the cation.
Cation. Good. If it is tetrahedral, what's the max ratio?
2:1.
And if it is octahedral?
1:1.
1:1. You got to remember that. All right. This feels like a lot just for that.
Yeah.
Here we are. All right. When an ionic compound is composed of cations and anions of similar size, basically a 1:1 ratio, it typically forms a simple cubic structure. So when the cations and the anions are basically the same as far as their radii, they typically form a simple cubic structure. Cesium chloride is an example of this. Cesium and chlorine have radii of 174 and 181 picometers respectively. Think of this as chloride ions forming a simple cubic unit cell with a cesium ion in its center. Okay, so you imagine a cesium, let's see. So we go back to this idea, right? So each of these is going to be chlorine. And it said with a cesium in the middle, right? Well, I've got chlorine's 1/8 of a chlorine in each corner, so that's 1 chlorine. I got 1 cesium in the middle, so I've got and 1 CS, so that's cesium chloride like that, right? I had it reversed, but right. Okay. So that's good. We understand that. You can also do it the other way. It could be cesium in the corners and it can be chlorine in the middle, right? So the orientation is somewhat random. Here, cesium ions and chloride ions touch along body diagonals of unit cells. One cesium ion and one chlorine ion are present per unit cell, giving the 1,1 stoichiometry required by the formula for cesium chloride. Note that there is no lattice point in the center of the cell. Cesium chloride is not a body-centered structure because a cesium ion is not identical to a chloride ion. Okay. We've said that the location of lattice points is arbitrary. This thing demonstrates that. When an ionic compound is composed of a 1-to-1 ratio of cations and anions that differ significantly in size, it typically crystallizes with a face-centered cubic unit, right? So this is another one. This is when cations. I'm sorry. Anions. Cation, no, needs to be smaller. Cations are greatly smaller than anions. Right, then in terms of their radii, then they'll typically form a face-centered cube. Okay. An example of this would be sodium chloride. Sodium has an atomic rating of 102. Chlorine has 181. We can think of this as chloride ions forming an FCC cell with sodium ions located in octahedral holes in the middle of the cell edges and in the center of the cell. The sodium and chloride ions touch each other along the cell edges. The unit cell contains 4 sodium ions and 4 chloride ions, giving the 1,1 stoichiometry required by the formula in HCl. Cubic formula for zinc sulfide, zinc blendate, also crystallizes is in an FCC cell. The structure contains sulfide ions in the lattice points. Radius of a zinc ion is only about 40% of the radius of a sulfide ion, so they're located alternating tetrahedral holes. There's 1/2 of the tetrahedral holes. There are 4 zinc ions and 4 sulfide ions in the unit cell, giving the empirical formula ZnS. This is just wearisome. A calcium fluoride unit cell is also a FCC unit cell, but in this case the cations are located on the lattice points. Equivalent calcium ions are located at lattice points of an FCC lattice. All the tetrahedral sites of the FCC array of calcium ions are occupied by fluoride ions. There are 4 calcium ions and 8 fluoride ions in a unit cell, giving calcium to fluoride ratio of 1:2, as required by the chemical formula CaF2. Close examinations will reveal a simple cubic array of fluoride ions with calcium ions in 1/2 of the cubic holes. The structure cannot be described in terms of space lattice of points on the fluoride ions because the fluoride ions do not all have identical environments. The orientation of the 4 calcium ions about the fluoride ions differs. My goodness, why do we care about that? Let's look at